Okay, now I cannot see you anymore. Anybody, I can only see my slides.
Okay.
I hope you will stay there.
Okay, now I will keep my microphone closed, but let me just say give some directions here.
Let me briefly try to help. So since you have a PDF presentation, you can upload your presentation, and then you present inside the system if you prefer. So then you can.
Do you know where to click for the uploading?
I think there is a plus.
Should I stop sharing that?
Yeah, I think.
Yeah, you stop
I don't
sharing.
think you need to stop.
No.
So there is a plus on your left hand side, I guess, so you can upload presentation, something like that. Can you find it?
On the left or the right?
I don't know. In my case.
Doesn't she have to be the host for that?
No, I don't think
no,
so.
Just the presenter.
I can make you the host.
Because I tried.
Now you are a moderator too, so.
I'm not finding it. It's the first time I'm using this, so.
Yeah, I tried that last week with Ceridonio, and we couldn't find a way of uploading.
Yeah, but my student usually.
Yeah, but I recall that it was very visible, the thing for uploading, and I don't see it anymore.
Okay, do not worry. So I think you can.
And so when you upload,
yeah, now maybe I found it. There's a plus sign, then there is carregar uma apresentação.
Yes.
So maybe it's.
There you go.
Let me find. Because there are many menus, right?
Yeah.
And with the uploading, you can present and see the people at the same time.
Yeah.
Okay, it will be good. Yes. It's uploading, I guess.
The point is that when you have a PowerPoint presentation with animation and this stuff, the system sometimes messed up with your presentation. But in PDF, there is no problem.
So I don't know if it's done.
It's probably loading, right?
Well, it was. Oh, yes, it is converting the file. I don't know why.
Let's see what it's gonna do to the file.
Yeah.
She still have a copy.
Yes, of course. No.
Now you can. I think you can click on. Yeah, there you go.
Yeah, there you go.
Yeah, but I'm not seeing you because I changed it. I want to check what was happening with the file. Oh, now it is. Yes. Okay.
Okay.
So now you can see only my presentation, and that's it. Yes.
I can see everything, the presentation, and I can make it take the whole screen or what you are seeing right now.
Everybody can do this, so they can have your full screen. Yeah. Okay, good. Better like this. Thanks.
Okay. So this only works because it's a PDF. If it was a PowerPoint, it could not.
No, I prefer PDF because I use Linux. Then if I change computer and yes.
Okay. So if there are any questions during the presentation, please open your microphone and ask a question. If you don't have a microphone, just type the question on the chat, and I will ask the question for you. I will keep an eye on the chat. So it's a pleasure to welcome Professora Maria Carolina Oliveira Aguiar, who did her undergrad, her master's, and her PhD at Unicamp from 1996 to 2003. I didn't know that in 2002 she was in Tallahassee, where I did my postdoc. How long did you stay there? 1 year?
6 months.
6 months. Was San Luis?
Yes.
Okay. And then from 2004 to 2006, she was at Rutgers in New Jersey, working with Gabi Kotliar and Elihu Abrahams for her postdoc. And you got the position at UFMG right after you came back. So since 2007, then you are at UFMG, right?
2006, yes.
2006, okay. So today she's going to talk to us about non-equilibrium dynamics in strongly correlated systems. And the microphone is yours. Thank you very much for accepting the invitation to talk to us.
Okay, I should thank you for the opportunity to give this talk. So thanks for the invitation. Okay, so I will talk about non-equilibrium dynamics in strongly correlated systems. Here's the outline that I will follow. I will do a brief introduction about quantum quenches and effective light cones. And then I will talk a little bit about two works that we've been doing in my group that we did, indeed, because there are papers published about them. So in the first one, we connected two spin chains, and then we watch how the magnetization evolves with time. And we will see the appearance of effective light cones, and the boundary of these cones are defined from different types of excitations. Can be spin-on or a bound state excitation. In the second work, I will spend more time in the second work, we connect an impurity to interacting chains. We also see effective light cones, but more interestingly, we saw that the magnetization at the impurity side decays as a function of time, and it decays faster if we increase the interactions in the chains. Okay, I will give more details along the talk. Okay, so the first thing is I want to, sorry, no, it is right. I need to use the mouse and not the keyboard to change the slides. Okay, so I want to define what a quantum quench is. So initially we prepare the system in a given eigenstate of an initial Hamiltonian, and then suddenly we change the Hamiltonian and look how the system evolves with time with this new Hamiltonian, right? So the quench is that we change some parameters in the Hamiltonian, and then the initial state is not an eigenstate of the final Hamiltonian. Here is an example. It was realized experimentally. I will show you experimental results in the next slide. So the situation was like this. They first prepared this system using optical lattices in such a way that this barrier here was very high, so that the ground state had one particle per well per side. This is similar to a Mott insulator. Then they suddenly decrease the barrier so that the initial state is no longer an eigenstate of the final Hamiltonian, and they watch what happens as a function of time. Although Schrödinger equation is not relativistic, Lieb and Robson show that in many body systems with short-range interactions, there is a bound in the velocity of information propagation. This means that if we do something here in part A of the system, it takes some time for part B to fill this change in A. So that's why, in this case, we have the formation of effective light cones. Okay, so now we have the experimental results that I mentioned. So, as I said, in the beginning, the barrier was high, and then they suddenly decrease it. And the discussion they did in the paper was that they could understand what is going on as a function of time by defining two quasi-particles. The red one corresponds to two particles, and the blue one corresponds to an empty side. And they look how these quasi-particles become far apart as a function of time. They defined a correlation between these two quasi-particles. I do not want to get into the details about the definition, but I want to show you the results. So here we have the correlation as a function of time. I'm assuming you are seeing my mouse. It's a red circle and a hand.
Yes.
Yes? Okay.
Yes.
Hopefully it's moving as fast as I'm doing here, but okay. So this is the experimental result, correlation as a function of time for different values of the distance between the quasi-particles, and we see that the peak moves towards larger values of time as the distance becomes farther. Okay, we can put all these results here in a color plot. So the color here refers to the correlation as a function of distance and time, and then I hope you are convinced that we have an effective light cone in this case. So since this was an experimental result, we used this as a motivation for our theoretical result, theoretical work. Okay, and I will now start talking about the first of the two works that I want to summarize to you. So in the first one, we consider spin chains. I will get into the details about this. So initially they were disconnected, and then we connected them. This was a work done by two former students of mine, Alberto and Elena, in collaboration with Rafael, who is in the math department, and with collaboration with Rodrigo, who is in Natal. What we did first, so before the quench, we had two spin chains. One was prepared in a ferromagnetic phase, and the other one was prepared in a paramagnetic phase. And at t equal to 0, we connected them. It's a local quench because we just connected them here in the middle. Okay? Each of the spin chains is described by the XXZ model. It's an S.S type of interaction. One S refers to one side, and the other S refers to the neighboring sides. When we write down as a function of components, we have the X component, the Y component, and the Z component, in such a way that we can have the coupling in the Z direction different than the coupling in the XY direction. Usually we do this JXY equal to 1. It's our unit of energy, and we can change this coupling in the Z direction. Usually we call it the anisotropy parameter. So the goal of this work, I should have said before, is since one of the chains was prepared in a magnetic phase, we wanted to know what happens to the second chain, which was in a paramagnetic phase, after the coupling, after the quench, after we connected them. Since we have a magnetization in the left chain, what this magnetization causes in the right chain after the quench. This was our goal. So let's talk about the XXZ model. In one dimension, so we always have chains. This is because we use DMRG, density matrix renormalization group, to solve this problem numerically, right? So that's why we are always in 1D. And the good thing is that there we also know analytical results. So the XXZ model has an exact solution via bet ansatz in 1D. If JZ is very small, is smaller than -1, then we minimize energy by having two spins in neighboring sides pointing in the same direction. That is, we have a ferromagnetic phase. If JZ is larger than 1, it's the opposite. We minimize energy by having opposite spins in neighboring sides. And in between, if JZ is between -1 and 1, we have a paramagnetic phase as the one in the right chain. This is the Luttinger liquid phase. Through bet ansatz, we have not only the ground state, but also the excitations. We know the excitations. We can calculate the velocity of them analytically in 1D, and this will be important in our work. Okay, so here are already some of our results. In color, we have the magnetization, the expectation value for SZ, in the left chain and in the right chain. If you look here, the magnetization at the left chain doesn't change much. This is because this is a gapped phase. It changes more in the right chain as expected. Okay, as I said, we know from that ansatz the elementary excitations in both cases. In the case of the left chain, which is in the ferromagnetic phase, these elementary excitations are magnons. And we know their velocity. We can calculate the maximum velocities for magnons, and this is equal to jxy, which we do equal to 1. And indeed, if you see here, the boundary of this, so first of all, we see effective light cones in this case, right? And the boundary of the effective light cone is defined by the maximum velocities of magnons. Why is it maximum? We can have excitations with smaller velocities, but it's the maximum value that determines the boundary of the light cone. In the case of the chain that was in the paramagnetic phase, for this value of Jz that we are using here, elementary excitations are spinels. And as I will show to you, we have that the maximum velocities for spinels determine this boundary of the light cone. And indeed, we can find another kind of excitation that was the new result of our work, depending on the value of this Jz. So what I will do next is to change Jz. Okay, first, indeed, I'm showing the same value of Jz as before, but I'm changing the coupling in the left chain. Since not much happened over here, we can choose this to be deep in the ferromagnetic phase. Okay, so I'm moving this, instead of minus 1.1, it will be minus 20 deep in the ferromagnetic phase. And now I'm looking at the magnetization only in the right chain, because not much happens in the left chain. So this is the magnetization as a function of time and position in the chain. I think it's better to do cuts at fixed time. So this time here and this other one, that's what we see on the right. So we see the profile for SZ as a function of x for fixed times. At t equal to 0, the magnetization was 0 because we were in a paramagnetic phase, but for finite time, we have these oscillations of the magnetization. If we track the wave front, then from this wave front, we can define this solid line that we have in the plot on the left. And if we calculate the slope, the inverse of the slope of this line, right, because we have time here and x, we get the velocity that is defining this light cone. If we do so, then we can build a plot of velocity as a function of Jz. The one that I'm showing on the left is this one. It corresponds to the red dot here, not the square, right? So this comes from our numerical results out of equilibrium. And the dashed line here is the velocity that we get, the maximum velocities for spinels that come from the Bethe ansatz solution, from the analytical solution at equilibrium, right? So the circles, the symbols are our numerical results out of equilibrium, and the dashed line, as well as the solid line, are results from an analytical solution given at equilibrium. Okay, so as I said before, if we move for Jz, if we change Jz, another kind of excitation appears which has a larger velocity than those of spinels. This corresponds to this solid line over here and corresponds to a bound state excitation. So I will show you details about this case in the next slide. So let's change Jz. So Jz now is much smaller, is smaller than minus 0.3. And now I hope you recognize that the profile for SZ as a function of x changes. Before we had oscillations, now we have some oscillation here for larger values of x. So it's again the same thing. The color here is the magnetization as a function of time in x. Then we fix some values of time, and we have SZ as a function of x for different values of time. And so for larger x, we have some oscillation, and for smaller values of x, we have this large pulse here. If we track the wavefront, then this gives rise to this dashed line in the left plot. If we track the beginning of this large pulse, then this gives rise to this solid line in the left plot. We can again extract velocities that define these two lines, related to these two lines. And if we go back to the plot of velocity as a function of Jz, we are now at this value of Jz, and we have the two red circles, which corresponds to the first one, the smallest velocity, corresponds to the solid line here on the left, and the larger velocity corresponds to the dashed line on the left. Okay, and we did this for very many values of Jz. We did this also for the entanglement entropy. I'm not showing the results here because lack of time. And the results coming from the entanglement entropy corresponds to these squares in blue. And in general, we have a good agreement between the velocities defining the light cones and the velocities either of the spin-on excitation or the bound state excitation. So to conclude this first part, we did observe effective light cones both for the magnetization and the entanglement entropy, although I'm not showing you the results for the entanglement entropy. The boundary of the light cone is defined by different kinds of excitations. It can be a spin-on excitation or a bound state excitation, depending on the value of the anisotropy parameter. And in general, so these excitations we know from the situation at equilibrium, and we got the light cones in an out of equilibrium situation. So we can conclude that the equilibrium properties manifest in the out of equilibrium dynamics. So now I will move to the second work. Let me just get some water. In the second work, we consider it's again a quantum quench, right? But now we consider a spin or an impurity coupled to interacting leads. This work involved Helena, who is now a professor in Brasilia, Mo Alisson, who is a current student of mine, also Rodrigo, who is based in Natal. So indeed, Helena got numerical results, and Mo Alisson got analytical results under the supervision of Rodrigo. Okay, I know some of you are expert in the Condom effect, but probably there are students in the audience, so I will spend a couple of slides making an introduction to the Condom effect. So we know since the early 1930s that the resistivity of metals with magnetic impurities presents a minimum. So this is a sketch. It's the resistance as a function of temperature. For a regular metal, it's the curve in blue. So it goes to a constant as we decrease the temperature. For a superconductor, it goes to 0 below a critical temperature. And in the case of a metal with magnetic impurities, we have a minimum. This can be seen in this real results here. Real, it's for a material. It's iron in molybdenum and niobium alloys. So as the concentration of molybdenum increases, we clearly see the presence of a minimum in the resistivity. So Condom was able to explain the presence of this minimum and also a behavior with temperature that goes with minus ln of T by using the Condom model. So the Condom model has a term which is similar to the one that we had before in the XXZ model. It's a term where we have an S.S interaction, coupling. Now, one S comes from the impurity, so this D here represents the impurity because electrons in d orbitals usually are more localized than s or p electrons. That is, they form local moments, right? So this is corresponds to the spin of the impurities, and they are coupled to an effective spin coming from conduction electrons, with give rise to this other S here. So it's like an S.S coupling. By solving this model using perturbation theory, Condom got this minus ln of T in the resistivity. Putting together other contributions, like the one coming from electron phonon scattering or a T independent impurity scattering, then we understand that there should be a minimum in the resistivity. Okay? But if the temperature keeps becoming each time smaller, then this minus ln of T would give a divergence of the resistivity, which we do not see. And we do not see because perturbation theory breaks down at very small temperatures, at temperatures smaller than a characteristic temperature that we will call the Condom temperature. Perturbation theory breaks down and a new physics is coming into play. There is the formation of a singlet state between the spin and the conduction electrons. And then the resistivity does not diverge, and we also have the presence of a resonance at the dense of states. So the situation that I'm describing can be represented in terms of energy. We have energy here in the y-axis in this picture here. So for the impurity, we have energy levels. It's not a band, it's an energy level. If we have only one electron at the impurity site, it has an energy epsilon d. If we have two electrons in the impurity site, the energy is epsilon d plus u, where u is the interaction between the electrons. Later, I will take this quantity to be ud, okay? But here in this picture, it's just u. It's the interaction between electrons at the impurity site. And the impurity is in a metallic host, so the metal is represented here by this band, okay? And there is some hybridization between them. So if we look at the density of states as a function of energy, because of this hybridization, we have that the density of states has two bands, one around epsilon d and another one around epsilon d plus u. This is for temperatures above the Condom temperature. As we decrease the temperature, then we can have this singlet, the formation of a singlet between the spin of the impurity at the impurity site and the conduction electrons. And this gives rise to this resonance at the firm level in the case when we have this Condom effect. We have the formation of the singlet state. I'm telling about the density of states so that we can understand the next result. So this is a much more recent result. There was a renewed interest in the Condom effect because it was seen in quantum dots. Okay, so we can go to the lab. We can confine the electron movement, for example, into a plane. This means we confine it in one dimension, and so that the electrons can move in a plane in the x and y direction. This would correspond to this red region over here. And we can put some contacts, and we can confine the movement in the x and y direction as well, in such a way that we have a quantum dot, what is called a quantum dot. It's like an artificial atom because there is confinement in all the directions. And if it's like an atom, we again have energy levels, not bands, right? The energy is well defined. And it's a similar situation as before. So the quantum dot here, the electron that exists here is like the impurity, and it's coupled to conduction electrons through these contacts. The number of electrons in the quantum dots changes when we change the gate voltage, so we can have the situation with an odd number of electrons in the quantum dot. And if this is the case, we have an unpaired electron there that can form a singlet with the conduction electrons at very low temperatures through the Condom effect. And according to my last slide, this gives rise to a large density of states and thus to a high conductance in this case. And indeed, if we go to the experimental results, this is conductance as a function of gate voltage. In this case, here we have an odd N, and the conductance is high at low temperature. So the blue curve here corresponds to 25 millikelvin of temperature. As the temperature increases, then the conductance decreases because there is the singlet that was being formed through the Condom effect is destroyed, and the conductance decreases. Okay, so I do not have this configuration in my work, okay, but in this kind of experiment, they have a good control on the parameters of the system, and this motivates us to study a situation out of equilibrium, which is a more complicated one, okay? So now I will start really talking about our work. There was an introduction about the Condom effect that we would like to see in our case. Okay, in our work, we consider an impurity coupled to two wires. Indeed, it can be one wire or two. I will show you results for the two situations. So we turn on, so initially the impurity is not coupled to the wires, and at T is slightly larger than 0, we turn on the hybridization. That's why it is called a hybridization quench. Okay, so we turn on T1 prime and T2 prime at T a bit larger than 0. So in one situation, we turn on only T2 prime. In the other one, we turn on both of them, okay, in such a way that we have only one wire or two wires. Note now that the energy level of the impurity site is epsilon D as before, but the interaction at the impurity site is UD. This is because we are using U to refer to the interaction in the wires. So if we have electrons in the wires, they are also seeing each other, they are also interacting between each other through an interaction equal to U. And indeed, that's what we want to see, because usually in the Condom effect, the coupling of the impurity is to a non-interacting electron system. And now we want to study the role played by the interaction in the wires in this situation, in this non-equilibrium situation. So we want to see what happens with the Condom effect in the presence of these interactions in the wires. T here is the hopping. So the electrons can hop from one side to the other, and the probability of this hopping happening is given by T. I think the next slide is indeed the Hamiltonian that we use to describe this system. So we have one term coming from the two leads, wire or leads, one term coming from the impurity side, and also the hybridization between them. So since we want the wires to have to be an interacting systems, we use the Hubbard model to describe them. So here is the Hamiltonian for the Hubbard model. That's the one that we use to describe the wires. So this C is it destroys, with this C we destroy an electron at site I plus 1, and with this C dagger we create an electron at site 1. So this means that the electron can hop from one side to the other in such a way that this whole term here represents the kinetic energy. The electrons can move through the wire. And the second term comes from the interaction. It's taken into account only when we have two electrons at the same site. So this N here is the occupation number at site. So only when we have two electrons with opposite sides, we pay an energy equal to U because of double occupants. So this was for the wires. For the impurity, we have the same thing as before. So if we have one electron at the impurity side, the energy is epsilon D. If we have two, it is epsilon D plus UD. Okay, now we are using UD for the impurity. And in the case of the hybridization, the electron can hop from the impurity side, which is the site equal to 0 here. It can hop from site 0 to -1 or to 1. The connection is only with the first sites in each wire. Okay, here I'm showing our first results for this case, numerical results. So I will go slowly because there are many results over here. So on the top, you can see the results for the change in the occupation. It's the change as with respect to t equal to 0. So in the beginning, there's no connection between the impurity and the wires. Then we turn on this connection and we are checking what happens with the change in the occupation, right? So this corresponds to the colors here. And in the y-axis we have time, and in the x-axis we have y, the position at the impurity, at the wire, or at the system, indeed, because we have, here we have both the left and the right wires. So on the top, it is the change in the occupation. At the bottom, it is the change in the magnetization. On the left, it is for u equal to 4, and on the right, it is for u equal to 8. So we are changing. Remember that u is the interaction inside the wires. ud, the interaction at the impurity side, is always equal to 7. At 1D, we know that there is charge-spin separation. This means that we have some excitations that carry only charge and other excitations that carry only spin. The ones that carry charge are called holons, and the ones that carry spin are called spinons. Okay, and what we see here, so first of all, we see light cones, effective light cones for both quantities, and but the boundaries of them are defined by different types of excitations. So these straight lines here, red straight lines in all the plots, corresponds to the velocities given by the BET ansatz now applied for the Hubbard model. So we also have analytical results, exact analytical results for the Hubbard model coming from the BET ansatz. And these are the results that we are using to draw this straight line over here. As we can see, if we change u, the interaction, the velocity for holons doesn't change much. Now here, I should say, as I said before, it's the maximum velocities for holon, right? It's not the one at small energy. Here, it's away from the small energy, but it's the maximum one that defines the light cone boundaries. The velocity doesn't change much with u in the case of holons, but it does change with u in the case of spinons. Another thing is that the velocity for holons is larger than the one for spinons. Remember that we have to take the inverse of the slope to find the velocity here. Why I'm comparing the two velocities? Because I'm now going to show you the results for the entanglement entropy. So at the bottom here, it's the same results that you saw in the last slide. The new result here are those for the difference in the entanglement entropy. So what we do here is we divided the system into two parts, the part A and part B. Part A takes into account the leftmost I sides, and part B takes into account the remaining sides of the system. And we want to see how they are, part A is entangled with part B. That's what we are calculating here. And we are looking at the change with respect to before the quench, right? If you compare, and this is different than the quantities that I showed before, because the quantities I showed to you before were local quantities. The occupation is a local quantity. It depends only on one side. But the entanglement entropy depends, it's a non-local quantity because it involves many sides, right? So this is the main difference between the two kinds of quantities. And what we can see here, if we compare, is that the entanglement, the light cone for the entanglement entropy is defined by the holon type of excitation, which was larger than the spinon type of excitation, as I showed to you in the previous slide. Okay, now let's focus on what happens at the impurity side. So here are results for the occupation at the impurity side as a function of time for two different values of ud and different values of u. On the right, we have results at equilibrium that we are taking here from a paper in the literature. If we compare carefully the two plots, I mean, our results with the equilibrium results, one of the conclusions that we get is that the occupation at the impurity sites approaches the equilibrium values. And this was expected because we had a local quench. We are not changing something in the system as a whole. We are, for example, we are not turning on a magnetic field everywhere. We are just doing some change in the system locally, close to the impurity, right? So we, in these cases, we expected that the quantities go to the equilibrium values, and that's what we see here in our results. Another thing is that the deviation from single occupants decreases as we increase U and UD. So clearly we see here it's very close to 1. The occupation here changed just a little. And if we increase U for small values of UD, we increase U, we again see that it goes to values closest to 1. This is important because we want to be in the Condom regime. We want to be in a situation that the Condom effect could take place. So we want to be close to this single occupants situation. Now I'm showing you the magnetization at the impurity side as a function of time, again for two values of U and different values of UD in each panel. We can see that again it goes towards the equilibrium value. Now here the equilibrium value is equal to 0 because of the Condom effect. If we fix U, so if we look at this U equal to 4, we get to the conclusion that the magnetization decays faster with decreasing UD, right? Decreasing UD corresponds to coming this way here, and the magnetization decreases faster. If we fix UD, say we look at the yellow curves, we see that the magnetization decreases faster for larger values of U. We want to understand better, so we see from the numerical results that the magnetization, the behavior of the magnetization depends on U and UD. U is the interaction in the wires, and UD is the interaction at the impurity side. Since we want to understand better these numerical results, we did some analytical calculations. In this situation where we have single occupants at the impurity side, we can get some effective Hamiltonian, right? This, if we take this limit here, I think I'm running out of time, so I will try to go quickly to the end here. So I don't want to get into the details about the analytical calculation, but I just wanted you to have an idea on what we did. So we want to be close to single occupants, so we took this limit over here, and in this case, the hybridization term between the impurity and the wires can be described by a Condom-like term. One spin comes from the impurity, and the other spin comes from an effective spin involving just the first sites in each wire, right? So we have now an effective Hamiltonian that we can treat analytically. So we use, there is this Condom part, but there is also the part coming from the wires, from the leads. And we use the Luttinger model to describe the leads. To solve this model, we use bosonization. We also write down the Condom part in the bosonized form. Then we do an expansion in powers of the Condom coupling. So there is this JK here, which is the Condom coupling in the Condom model. We can define another coupling, which is this lambda K, which depends on JK, as it should. But from this expression, we also can see that the coupling depends on 1 over UD. This will be important to understand some of our results. When we do all this treatment, we did this to get the magnetization. And I will show you now the result for the magnetization. The analytical one is this very big expression over here. I will try to explore it. So if we only have, this expression is to the case when we have two wires. If we have only one wire, wire, only the one on the right. Then we don't have this second term over here. We only have a term that goes with ln of tau. And we also don't have these two over here in the case of only one wire, right? When we have, in this term here, we don't have an explicit dependency on U, the interaction in the wire. But in the second one we have, because this Kc here is a Luttinger parameter that depends on U. It goes to 1 in the case of non-interacting system, but it is between 0.5 and 1 in the case of interacting system. So we get a term here that explicitly depends on U. I have to say that this expression is only valid in the intermediate time interval. Okay, this is because when we do this Luttinger model here, it is valid at low energy, so we have to introduce a cutoff in energy. This cutoff in energy is what we are calling lambda here, okay, and we can go to the space, to the time space, and this gives rise to this 1 over lambda that I'm showing you here. So since we are at the treatment is valid at low energy, this means that it is valid for tau larger than 1 over lambda. And I think you remember that I discussed the Condom temperature, which is a very low temperature. And from the Condom temperature, we can define a Condom time. And if the time is close to the Condom time, we know that we have to go beyond the expansions. We have to take into account more terms than those that we took into account over here. So that's why this result here is valid only for tau, much smaller than the Condom time. So it's valid for intermediate values of time. I will show you, I will now compare our analytical result with our numerical results, and I will do another approximation here. I will take tau much larger than 1 over lambda. Then the expression simplifies. Now we are looking at the results for only one wire. Then this is the simpler expression that we get. This is for the change in the magnetization, right? At t equal to 0, the magnetization is 0.5. So if we look at the change, that's what we have in the plots on the right. The plots on the left are the same that I showed you before. This is for comes from our numerical calculation. And now we plot the change in the magnetization as a function of 1 over ud squared ln of tau. So if this expression is valid, we should get straight lines, as we indeed get, right? In both cases, for u equal to 4 and u equal to 8. So our analytical results agree with the numerical ones. And now we can see, I said that when we decrease ud, the magnetization decays faster. And now we can understand, because we have this 1 over ud squared, or the magnetization depends on 1 over ud. That's why that it decays faster as ud decreases. If we compare the two cases, u equal to 4 and u equal to 8, we see that the slope of these straight lines are different. So this we cannot capture with our treatment. This means that probably the cutoff depends on u. It doesn't explicitly appear in our calculation, but it can be some dependency of the cutoff with u. If we go to the case with 2 wires, then this simplified expression is this one. Now we have the same term as before, the one going with ln of tau, and we have a power law that explicitly depends on u, the interaction in the wires, because this Kc here depends on u. But unfortunately, since we do it to the numerical calculation, we cannot go later in time, so we just have a limited time range, and then we cannot distinguish between a situation where only this first term is more important, or both terms are contributing to the final result. Okay, so although we get some dependency with Kc, when we compare with the numerics, maybe the most important dependency with U comes from this first term over here. So I finally get to my final slide. Sorry if I talked too much. So in the second work, I discussed this quench, where initially we had an impurity which was not coupled to wires, and we suddenly coupled the impurity to the wires, or to one wire or to two wires. I showed you results for the time evolution of the occupation, the magnetization, and the entanglement entropy. In all the cases, we saw effective light cones, and the boundary of these light cones were defined either by an excitation that was carrying charge or an excitation that was carrying spin. So for the occupation and the entanglement entropy, it was the excitations carrying charge, and for magnetization, it was the kind of excitation carrying spin. Now, if we look at the magnetization at the impurity site as a function of time, we saw that for fixed values of UD, the magnetization decays faster if you increase the interaction at the wire, in the wires. And if instead we fix U and see, analyze the situation for different values of UD, then we see that the magnetization decays faster if UD decreases. And this is in general accordance with our theoretical results. So thanks for your attention.
Thank you very much, Carol, for the very nice seminar. It's open to questions now. Does anyone have a question?
I do have plenty of questions.
Yeah. So, as soon as usual.
Nice talk, Carol. Very, very interesting results. I have.
Thank you.
As I said, I have a list of 7, but I'm afraid George will not let me. So I'll pick.
We have time. We have time.
All right. So my first question actually is closer here, and I'm probably missed something, is regarding the magnetization in this system. So
in the second work or in the first work?
In the second, right?
Okay.
Right.
So here's the definition that it's the expectation value of.
Exactly.
Okay.
So my question, I probably missed the initial state. You have a spin, right?
Yes, it's a spin up. Maybe I didn't stress that. Yes.
So I was surprised because this essentially.
It's here. The initial state, it's a spin up, and that's why the magnetization at t equal to 0 is 0.5.
So on this initial state, the system is not in the Condom regime, right? Because I mean. No.
The hybridization here is 0. So it's at t equal to 0. It's just one impurity and 2 wires or 1 wire. So it's not coupled to a metal.
Okay.
It's just a spin. It's just a single spin here.
So at t plus delta, the system still have a magnetic moment at 0. Not a magnetic moment, that's a magnetization, right? So
at time equal to 0.
Now t plus delta, just right after you couple the system, right?
Yes. Then that's what we have here in the plot, right?
Right. So in this sense, the system, let's call that way, free electron. It's not free. They are not free because we have a Coulomb interaction, but they are had not screened
the idea here, we want to get to the Condom effect, but it takes more time than the one that we have here, either in our simulation or in our analytical results. So the system is evolving towards the situation where we should have a screening of this initial state of this spin at the impurity, but we didn't get there. And unfortunately, we could not get there in the numerical calculation because of the situation gets there's some limitation in the time that you can perform the calculation here in the numerics, and also in the analytical one. So unfortunately, we didn't really go to the situation where there is a perfect screening, but we are watching what happens towards that.
Mm-hmm. So
okay, something is happening. The Condom effect is starting to appear, but we cannot say that it completely appeared here. We should go to larger times to see this.
May I ask or make a comment or ask a question? What do you have a feeling of why it seems that the Condom effect is developing faster when you increase U? Because that's what it looks like, right?
Yes.
The decrease of the magnetization is faster for U equal 8 than for U equal 5. Yes,
there's less change in this situation. There's less change in the system doesn't want to change much because there is U. Because we want to be close to single occupants, right here. So if we increase U, we are close to this situation of single occupants.
Single occupancy in each, you are at quarter filling, right? In the leads, in the chains. That's I remember seeing somewhere a quarter filling. Was that for the
quarter
leads?
filling? Yes. This is because yes, that's another thing that I should point out. We are at quarter filling so that we are in a metallic. The leads are in a metallic state. At half filling, we would have an insulator there.
Sure,
that's why we are at quarter filling. Yes.
Sure.
Okay. Yes. So it's harder to understand why, but it seems that with a larger U, there is less fluctuation.
Okay.
And this would justify why it goes faster. But
sorry, I interrupted.
No, that's okay.
Can I make my second question already? So I will leave you.
I just no. We can keep asking questions as much as we want. There is just let me see if this contributes to the discussion right now. There is a question from Luis Henrique Gessi. Do you have some idea how the Condom temperature changes with U? I assume, well, with U in the leads, right? Not with UD. Sure, yeah.
Okay, so...
That
yeah, so
probably is in that paper of Hiera and Gaza, right? Or not?
I think it should go similar to this expression here, right? Because this is the Condom time.
Okay.
Condom temperature, yeah, should be.
No, this is the time, right? Which is the inverse of the Condom temperature. So according to this expression, well, this is the cutoff that we are using, because here it's a wire, right? So it's not the same expression at higher dimensions for the Condom temperature. And well, in our calculation, we got to the conclusion that this lambda depends on U. But from the analytical point of view, yes, no, maybe it's this paper that you cited.
Okay. So this expression should give an idea of how it changes with U.
Yes, we saw that this here. So this A changes with U. This A depends on 1 over lambda, and it gets larger for larger values of U, right?
So what you are saying is that TK should increase with U. The Condom temperature should increase with U. That's what Because the
We have
inverse,
to invert many times here, right? So
yeah.
the A becomes larger when U becomes larger, but then lambda becomes smaller, and we have to invert lambda. It's so and then we have to invert again, right?
I am lost already. I am lost already. Well, but the answer to this question should be in that paper that you refer to by Hiera's group, right?
Yes, I guess so.
Right. That's an equilibrium result, right? That paper.
Yes. Yes.
Okay. Yeah. So
this one you mean?
Yeah.
Yeah, it's at equilibrium.
Okay. Yeah. Werneck, you.
Yeah. My second question is regarding the entropy. At some point, I plotted the light cone where I have the entropy and right there. So, technical question. This entropy is kind of I'm not really fond of calculation of entropy, but as far as I understand, entropy is you need to specify a link in the system. So you trace over the environment, say, and keep the link entropy essentially, right? It measures how.
Yeah. Well, formally, it's the entanglement entropy between two parts, right? Part A and part B, and that's it. It's defined by this expression here. I didn't explain because lack of time. This quantity here, I never remember the name of this Greek letter, are the eigenvalues of the reduced density matrix. So, and this, when we calculate this reduced density matrix, that's what you are saying. We are tracing out one of the parts. But indeed, this is the same for both, right? So, if you want to do the one for part A, you trace the one of part B or the opposite.
Right. So here you calculate at many positions. So we make it.
Yes. Why here is changing? So the partition A is increasing and partition B is decreasing. That's what the meaning of this x-axis over here.
Last question in this slide. Why the left right is not symmetrical in the bottom panel? It shouldn't be. Why the left
well,
right is different?
There's one detail here, because when we do DMRG, usually we want to be always with even number of sides, right? So since we have the impurity over here, then the impurity is one of the sides, and then we don't have an equal number of sides in the two wires. One has 23 and the other one has 24. That's probably the reason why it's not really symmetrical here. Okay. But this is I mean, it comes from the implementation that we did. We want to do a better implementation where maybe we could have an odd number of sides in the system as a whole, but we didn't get to there. So it probably comes from it.
Great. Thank you very much.
Geneton has a question. He will turn his mic.
Okay. Thank you for the nice talk. Actually, my question is just asked it. So but okay. But anyways, I can ask another one. So actually, you have two different chains, right? On the left and on the right of your input side. And you said that in the end, you were trying to find the Condom regime, right? Looking for the magnetization. So my question is, could you also make an extension of these chains, for instance, make it like infinite, and try to map to some analytical results, which I think would be much easier than to consider the system finite? No, indeed, it is finite in the numerics. Sorry, it's finite in the numerics. In the analytical situation, it's infinite or same infinite. Okay. Yeah, because I mean, this way you could get at least a glimpse of what's going to happen in the infinite case.
No. To do the analytical calculation, we took this limit of L going. That's why I was at some point I want to say wire. Usually I say chain here and wire when it was same infinite.
All right. Okay. Thank you so much.
Okay. You are welcome.
I have a question. Well, there is another question here. Before I ask, Luis Henrique is asking, I don't know what he's referring about this. This must not be the reason to the magnetization changes faster with U.
I think it's because he was commenting on the Condom dependence with U.
Probably, yeah.
Can I say something? My question is, I asked this again when you were discussing about the magnetization and the dependence of the magnetization with U. So I expect that this dependence vary with the Condom temperature. And this is why I asked how you change the Condom temperature. That this was my point. And this was my motivation to ask about the Condom temperature. Just it. Thank you.
Yeah, I mean, we really didn't get to the point where the screening was perfect, right? I think at some point we want to try to extract the Condom temperature, but then we got to the conclusion that it didn't make sense because of this, because we really didn't get to the limit where it is really formed. This in our results, in our numerical results. Of course, there are some analytical expectation for that, and I think it is related to that equation that I showed. So I mean, this equation was written coming from the expectation of the dependence of the Condom temperature for this case.
Luis Nunes wants to ask a question.
Yes, thank you. Very nice talk, Carolina.
Thank you.
Thank you. All right. Actually, there's two questions. One is, it's a comment, and I'd like to hear your opinion about that. If you were carrying out this calculation for U equals 0, which would be the regular Condom problem, these lattice sizes would be too small, right? There's no way you could see Condom scaling with 25 or 26 lattice sites, because everything scales logarithmically, so you need much bigger lattices to see the Condom effect develop. Since you are seeing something which looks like the Condom effect here, this means that it's not scaling logarithmically. It's probably bunched up somehow. Scales are tighter because U is not equal to 0. And that is in line with your finding that it decays faster as U grows, right? So would you agree with this?
Yeah, I think it's a good point, yes.
Okay.
As we increase U, we go closer to, and this indeed U helps going towards the Condom limit. Yes, I agree. Yeah. Is this the conclusion? Yes. Yes. Okay. Yes.
All right.
Having U helps. Yes.
Okay. Now, the other question is about the first part of the talk. Can you say something about the physical meaning of that parameter J star? You have two branches of the...
Yes, yes.
Okay. Yeah, over there.
Let me try well, it is related to the point where the bound state, the velocity for bound state becomes larger, that it's defined like this, right? This situation where we have this bound state excitation, the velocity corresponds to it becoming larger than the velocity for spinons.
Yes.
A physical reason for this? No, I don't remember. Yeah, this bound state is like, because we can go to instead of discussing the model in terms of spins, this is equivalent to a spinless model. And so if we go to this particle model, this bound state would correspond to something like an exton. It is there's an electron and a hole that are bounded. That's why we call a bound state. But why exactly? I don't know if it's easy to know. We should ask Rodrigo if there is a simple way to see this, because if you go to the analytics, it's not easy, I think. So maybe there is a physical reason.
Okay. Okay. Thank you.
Thanks for the questions. I will open the paper here to see if I can find some explanation. Because you have to take the dispersions for both of excitations and calculate the maximum velocities. It's the maximum one, and indeed it's the coupling there, which in the paper we call delta. That's another way to call the anisotropy parameter. Delta star is exactly equal to cosine of 3 pi over 5. So there is a reason for this, for being exactly like this. I'm trying to find if there's a physical meaning. One thing is that it's not at k equal to 0. It's not an excitation that exists at small energies. So the maximum velocity is seen away from k equal to 0, and we have to find this. So the expression for the dispersion is a big one. It's not a simple one. So I don't know if there's a simple physical explanation.
Okay.
Okay.
All right.
Thank you.
Okay.
Just adding a comment to what Luis just said. Would it help, and this is a question to Luis too, would it help the numerics if you change your parameters in a way that the condo temperature is much, much higher? Because then the condo cloud would be much smaller, and maybe you could fit it inside the your numerical system. Would that help? Or you wouldn't be able to get to this regime where decay is high enough? Yeah.
I think you need to go longer in time.
Say that again?
I think you need to go longer in time.
In time, if you increase decay. Okay.
My question.
Yeah, but I think George's comment is his point is well taken. Maybe there is some other problem that you might have if you make the condo coupling too strong. But otherwise, this makes a lot of sense.
Because you could even study, you could change a little bit the parameters and make the size of the condo cloud increase and see how this would affect your whole, because you would have the condo cloud and the rest of your system outside of the condo cloud, but then you could have changing the parameters to make the condo cloud advance farther away into the rest of your system and see how this would change the physics you are seeing. Okay. So
yeah, but which parameters could we change over here?
You would have to make UD smaller and the coupling much bigger.
Yeah, but if UD is smaller, then we are farther from, where is the plot? UD smaller is this situation here.
Yeah.
Okay,
yeah.
maybe if we choose U very high,
Mm-hmm.
yeah, we decided to stay with UD at least equal to 5, so to be sure that we had a single occupants. So unless we could change U even more, right?
It's true that if you increase the hopping T1, T2 prime too much, you're going to start having mixed balance too. So you are not
that's
really
why.
in the Condom. But that's an interesting problem too, because you are in a transition from Condom to mixed balance. This could be interesting too. And if it helps the numerics, then maybe it would be worth trying. I don't know. It's just a thought.
Yeah, yeah. Maybe we can play a bit more with the parameters. Yes, trying to help the numerics. Yes.
Could you show, if there are no more questions from anyone, could you show the results where you show the cones for this second part? Yeah, there. Both of them. Maybe I am being. This is just numerics. I'm being picky, but it looks like you are at close to the impurity. You are having a velocity that is higher than the velocity that you get for the Holland velocity, which I assume is the maximum velocity, because you see these little bands that come down.
Here, you mean?
Yeah, it's there, but it's here too, close to the impurity. In the when I say here, is the plot right below this one. See that close to the impurity? Yeah, if you are far from the impurity, it seems that there is a very good agreement between what you get for the velocity from the blue and the red line. Yeah, and the red line. But you have some, it looks like it leaks out, indicating that either is numerics or you have a faster propagation than the velocity of the hollow. And this maybe is more, you can see this better even in the top plot for this is for the entropy, right?
Yeah, the top one is the entropy.
Yeah, but it could be numerics but I don't know. It looks like close to the impurity, you are getting faster propagation than the Holland propagation.
Yeah, I would say is some numerical.
Is some numerics.
Precision,
okay.
Right?
Okay. Okay.
Because there should be some error in the numerics. So, okay. And these are blue. So blue is very small, right? So okay. I don't know. Maybe it's
just the
error bars.
Okay. Okay. My other question is, if you go to the drawing with the model with the chains and the I don't know if you are if you have thought about the possibility of trying to investigate the two-channel Condom with a similar model.
Yes, it was one of our ideas, but we didn't get there. I mean, this work started when Elena was a student of mine, so we started this like 3 or 4 years ago. And then what we wanted to understand better the behavior with UD and U. So for some time we didn't publish these results, only the numerical results. And then Mo Alisson started the PhD with me, and we were discussing. Indeed, I present these results in a workshop in Paris, and an Italian guy said, "Look, I did a similar situation for the spinless case. And I think in your case, you can do a spin-full model and get some analytical results." And then Mo Alisson, my student, did this calculation, and so we finished with this. And this paper was published this year, in the beginning of this year. So, and Elena was under maternity leave, so she was not doing calculation for the last couple of months, and we didn't have time to keep going. I mean, Mo Alisson is doing some analytical calculation because he likes better to work with analytics than numerics. But in the numerics, no, we didn't. Maybe we will do it, but we have to see who will be able to really carry the calculations.
Okay. Okay. Well, let me see here if there are other questions.
Jorge, I just have one more. Yeah, but it's just but it's just a technical question. How did you solve the problem of the time dependence? I mean, what scheme did you use?
Suzik Trotter.
Okay.
Okay.
Thank you.
My comment, George, is that in the two-channel.
My 10th question.
No, my fourth question.
I'm just kidding.
No, but this is a comment. It just counts. So my comment on your question is that in the two-channel model, probably TK is smaller, right?
Well, I am not very familiar with the two-channel Condom, but I thought about it because you have this U in your electron reservoir, in your electron Fermi sea, and that's what Goldhaber-Gordon did with one of the Fermi seas. He added a charging energy to make it distinct from the other channel. So you could have a difference in U, a much smaller U in one side and a larger U in the other, so that you distinguish the two channels, and then maybe you would get the two-channel Condom. But Ricardo, if TK, maybe, I don't know if Luis is still there. Maybe Luis knows that.
He's still around. So one of the wire would be the box, right?
Yeah, the box that Goldhaber-Gordon built, and the other one would be the leads that would be the second channel. But I think that Luis is saying something.
No. I'm agreeing with you. Yeah, this would be an interesting problem to try out with an understand.
A much harder one, I believe, right? Because the ground state is not a Fermi liquid, and
fine-tuning of the parameters.
Yeah, you would have to fine-tune the parameters, but this would be really very interesting.
Right.
So if there are no more questions, apparently not. We should thank Carol again for the very nice talk. I'm gonna be writing you an email asking for the slides. Very nice slides too.
And I will write you to send my other question.
my other.
Problem. If you want to make the questions now, that's okay for me. We can stop the recording and you can make the questions. Only us will know about it, not everybody.
Yeah.
That will see the